So as we're looking at area between two curves, one of the things I told you we would run into when we were talking about this yesterday was this idea of functions that intersect each other more than twice. Okay, when we were looking at problems yesterday, we talked about this idea of area enclosed, or here you see the term the area of the region between the graphs. Okay, and we said that the intersection points are the points that define those. Okay, so if I were doing this one and I didn't see the graph here yet, what's the first thing that I would need to do?
Find the intersection.
Yeah, I would have to find those intersection points. So I would set f of x equal to g of x. Alright, so I'd have 3x cubed minus x squared minus 10x equal to a negative x squared plus 2x. Alright, I would need to do this first. But I would notice, okay, wait a sec, I've got an x cubed here, which means I'm going to get 3 answers. Alright, so as I'm solving this, I have a 3x cubed. If I add x squared to both sides, that actually cancels out. I subtract a 2x from both sides, so I have a minus 12x, and that equals 0. Okay? So now I'm solving this equation. I've got a 3x as a common factor, and an x squared minus 4 is left over. So what are my answers here?
2, negative 2, and 0.
Yeah, we've got 0 and plus or minus 2. So we've got three different intersection points. So what that tells me here is that if these are intersecting 3 times, that between 2 of those points, one of the functions is going to be on top. Between the other 2, or the middle one and the other one, the other function is going to be on top. Okay? So in order to do this, I want to figure out which one is on top in each interval. Okay? So I'm going to be doing 2 different integrals. One from negative 2 up to 0. And then I'm also going to do an integral from 0 up to positive 2. Now, if I simply plug in a number in each of these intervals, I'll be able to figure out which one is on top. So for example, negative 1 is between negative 2 and 0. If I plug a negative 1 in here, I have negative 1 minus 2, so that's negative 3. If I plug a negative 1 in here, I have negative 3 minus 1 minus 10, that's negative 14. Okay.
No, wait, that's not minus 10. That's plus 10.
Oh, plus 10. Yeah, sorry. So negative 3 minus 1 is negative 4, plus 10 is 6. So 6 is greater than that negative 3, so the f of x is on top. So in this one, I'm going to do f of x minus g of x dx.
There was a very similar problem in the homework, and they figured out that in that case the function was odd, and so that we could just combine those integrals. How do we do it here?
Well, this one, it's not odd.
When I solved it, it appeared that we actually can solve it as like 2 integrals of from negative 2 to 0.
Well, what would have to happen is when you did f of x minus g of x, the resulting function would have to be an odd function. And then you could just double it. Okay? But in this case, I don't know off the top of my head if that actually happens or not. My guess is by the time you figured it out, you probably could have just done it, Because
when we're doing it the regular way,
it becomes huge because it's two integrals.
Well,
And
let's take a look at it. If we have g of x minus f of x over here, I know if they're overlapping and then coming back to intersect, you know, if I plug in a 1, which is between the 0 and the 2, 1 or 3 minus 1 minus 10 is negative 8. Negative 1 plus 2 is 1, so g is greater than f of x, so I'm doing g minus f in this interval here. Okay? Yeah, question, Davi?
Okay, so you said last class that you're going to take, I don't know what it's called, but two straight lines up.
Absolute value?
Absolute value of the difference. And then so it doesn't matter which one you put on top and which one you put on the bottom.
Yeah, mathematically speaking, we could. Now, again, just to kind of show that we know what we're talking about, it's nice if we don't need to bother with the absolute value. We could, if it's a real quick check to just see which one is on top. But you're right in the sense that if I accidentally mixed it up,
But it does take time
okay,
to plug in the numbers.
a little bit, yeah, a little bit.
So like this, in this case, it's easy because it's between 0 and 2 or negative 2 and 0. But what if it was between negative 90 and negative 80? You have to plug in.
Oh yeah, and you'd have to plug in like negative 85 or something.
Yeah, exactly.
That's where, yeah, you might want to just not worry about it, go ahead and do the absolute value at the end. That's fine. Okay, it works. Alright, so at this point, f of x minus g of x, we've got a 3x cubed, we have a negative x squared minus a negative x squared. Well, that's 0.
Oh, it's because it's minus a negative.
Minus a negative.
Yeah.
And we have negative 10x minus 2x, that's a negative 12x. Okay? So I'm taking the integral from negative 2 to 0 of that.
Holy guacamole, it's an integral.
Okay?
Forgot it's an integral.
Now, the other thing, guys, think about this. Alright? When I do g of x minus f of x, I'm just going to get the opposite thing, right? So don't think too hard here. It's going to be a negative 3x cubed plus 12x. Okay? So it's not too hard here to do both integrals. But now what we'll do is we actually will integrate. We have 3x to the 4th over 4 minus a 6x squared. We're going to evaluate that from negative 2 to 0. But we also have a negative 3x to the 4th over 4 plus 6x squared. And that we're evaluating from 0 to positive 2. Okay? The nice thing about this is that when you evaluate both of these at 0, it's 0. Okay, so in this case, we're going to have 0 minus, and let's see what we get when we do negative 2. Negative 2 to the 4th is 16. 16 over 4 is 4, times 3 is 12. Minus 6 times 4, so that's minus 24. Okay? So that's this first one, so minus a negative 12 is positive 12. Okay?
The other one is the same.
The other one ends up being the same?
Yeah.
Okay. We know it's going to be minus 0 at the end. So we have a negative 2 to the 4th is 16 over 4 is
Negative 12.
is 4, so that's a minus 12. And then here we have 6 times 4, which is 24. Okay? So this is 12, 12 and 12, and that is 24. Okay? Now, actually, now that I've seen this one fully here, if it's symmetric, if our intersections are at the origin and then symmetric to the origin, we will get an odd function every time.
What do you mean symmetric to the origin in this case?
Here in -2, +2, they're an even distance away from the origin. Okay?
We're talking about only about x's, we don't even care about the function.
Well, yeah, because think about what we're doing. For it to be an odd function, when you plug in -x, you get negative f of x. Okay? Well, here we made it's f of x minus g of x, and g of x minus f of x.
Yeah, but if we put in the variables, if we evaluate for f of x for x, then these are not going to be odd functions.
Well, let's see. If I plug in a negative, notice if I plug in a negative in 3x cubed minus 12x, I get a negative 3x cubed plus 12x. So that part is odd.
That's because
Okay.
I was looking at the x squared, and because of x squared, I thought that both functions are not odd, and that's
Oh, okay.
I was confused.
Yeah. So actually these two different integrals are a reflection of each other about the origin. That's not always going to happen. It happens here because we're going from -2 to 0 and 0 to -2. Okay.
Mr. Hicks, oh, yeah.
So here we have some things to remember, and one is exactly what we're dealing with, but I also want to extend this beyond just what we're dealing with here and show you how we could also, if we have functions that are defined in terms of y, we can actually, instead of looking at top and bottom, we can look at right and left. Okay? So here's what we were dealing with already, the top curve minus the bottom curve. Okay? We have this function here, and okay, if we're going from A to B, then sorry, there's one function, and then let's say we've got this. Okay, we're going to be doing, let me get a highlighter instead. We're going to be doing this minus this bottom part to leave just what's in the middle, okay? And that's how we're getting, that's how we're getting just this piece here, okay? However, another way you could do it is with horizontal rectangles, okay? And this is going to be important when we get to the washer method. We're going to start with the disk method here on in a little bit. When we talk about the washer method on Friday, we're actually going to be rotating things around horizontally, and we'll actually have to use this. But notice this is going from two different y values for our integral. Okay? So yes, we're going to find the intersection points, but we're going to be looking at what those y values are. Okay? And notice our functions are going to be defined in terms of y's. Okay? So for example, we might have f of y and g of y, and we're integrating with respect to y. Okay? Now let me just illustrate what this is going to look like here. So here's y, and we could call this the g of y down here. All right? Which is the x. Okay? So again, let's think about two functions here. And what we would do is we would look at the intersection points and look at what the y values are in those cases. So here's our y1 and here's our y2. Okay, I'll zoom a little bit in so we can see better. So now, check out what happens here. If I'm looking at this as a rectangle, okay,
What?
all right, the height of that rectangle is going to be a delta y, okay, and let's say that, you know, this is our y sub I, okay, then the length of this rectangle here is going to be whatever the right hand one is evaluated at y sub I minus whatever's on the left evaluated at y sub I. Okay? So, this bottom one is, well, let's make that, well, we'll leave it. Let's make this f of y, all right, and this bottom one is the g of y, okay? So this point right here is the point and it has an x coordinate of g of y sub I, okay? And this point over here on the left is f of y sub I. And I would have to subtract those to get the width of that rectangle. Okay? So notice it's the one on the right and the one on the left, minus the one on the left. And notice I'm integrating with respect to y for two different y values, and those are the bounds. Basically, it's the same thing that we're doing, we just turned everything on its side. Okay? And again, we would have to have functions that are defined in terms of y instead of functions that are defined in terms of x. Okay? Let's look at that a little bit more closely here, okay? With an example that's not just theoretical, but actually has some equations, all right? So let's say that we have the region bounded by the graphs of x equals 3 minus y squared and x equals y plus 1. Well, you'll notice here, if I were to graph those, obviously I'm not dealing with functions here. They're not necessarily functions. Because as you can see, 3 minus y squared is this horizontal parabola. Okay? And we're trying to find this area enclosed right here. Okay? So, notice that in this case, the 3 minus the y squared is the one on the right. Okay? Here, okay, this is saying that we're letting g of y be the 3 minus y squared. Okay? Here is the x-coordinate that f of y equals y plus 1. Alright? So just dealing with this rectangle, if I did g of, what does that look like, 3? Okay? g of 3, so 3, or I'm sorry, the y coordinate. You know, let's say that that's at negative 1/2. Okay? If I do 3 minus 1/2 squared, I've got a negative 1/2, and then g of that 3 minus 1/2 squared is 3 minus 1/4, so that's 2 3/4. Okay? So right here, this is at 2 3/4. I'll write it this way instead of as points like this. Okay? Here, if I plug it into y plus 1, negative 1/2 plus 1 is going to be at 1/2. So the height of this rectangle is 2 3/4 minus 1/2. That would be 2 1/4. This way. Okay? So it's the same thing again that we did with the other one. We're just doing them sideways. Okay? So, now that all to say, we can tell just from what we just did here with the negative 1/2 that the 3 minus the y squared is going to be to the right. Okay? So, if I'm going to do the integral, I'm going to do the integral from y is negative 2 up to positive 1. Notice here, negative 2 to positive 1. Of the 3 minus y squared minus the y plus 1. Okay? So, right minus the left. Okay?
Is it dx or dy?
dy, yeah, sorry. Yeah, dy. So I'm integrating with respect to y. So integral from negative 2 to 1. 3 minus 1 is going to be 2 minus y squared minus y dy. And that's going to give us 2y minus y cubed over 3 minus y squared over 2 evaluated from negative 2 to 1.
Mr. Hickson,
Yes.
why are we using the y value instead of x value for the 1 and negative 2?
Well, actually, you'll see why when we look at the alternative. If we try to do this one vertically, it presents some challenges. Okay?
Oh.
We just.
So- Alright, so let's just finish this real quick. If I have 1, then I have 2 minus 1/3 minus 1/2. If I plug in a negative 2, I'm going to have a minus 4 plus 8/3 and minus 2. Okay? Don't forget to distribute the negative when you subtract here. So I have 2 plus 4 plus 2. That's going to be 8 minus 9/3 minus 1/2. So 8 minus 3 is 5 minus 1/2. There we have 4.5. Okay? So what's the alternative here? The alternative is trying to do this vertically. Okay? And again, this is why, Chloe asked, why don't we just do it like normal? Well, we're not dealing with functions here. At least this one, the 3 minus y squared, is not a function, so it poses some challenges.
But you can cut it in a function.
It's not.
You can cut it into functions. Look at what we do over here. Okay? If I were to solve this for y, that's easy. It's y equals x minus 1. Okay? However, if I tried to solve this for y, I'd have y squared equals 3 minus x, and then y would be plus or minus the square root of 3 minus x. So notice what I have now. I don't have just two functions. I have three different functions. Okay? So what we would have to do, we would have to see, okay, the intersection point, which we had already seen before, is at this point 2, 1. Okay? If I'm going to do vertical, then as I go from -1 up to 2, notice the top function is that y equals x minus 1, and the bottom function is going to be the negative square root of 3 minus x. Okay? So for that portion, I would be doing the integral from -1 to 2 of the x minus 1 minus the negative square root of 3 minus x.
Yes.
Okay? So the negative is this one down here. If I change colors, okay, the positive one is this up here. Okay? Again, I now have three different functions that I'm having to deal with. Okay? And not that it's horrendous, but it does just add a level of complication to things. Then I would have to do the other part. I would have to get this area over here, in which case I'm adding the integral from 2 to 3, because this point over here is the point 3, 0. But notice what I'm doing. I would have to subtract the square root of 3 minus x, that's the positive, minus, on the bottom I have the negative square root of 3 minus x dx. Okay?
The y is like, oh, so the bottom is the, like the negative function, the opposite is the positive.
Yeah, there is symmetry here, if you saw it.
Okay.
And that's why minus a negative, that, in this case, it's going to make it the integral from 2 to 3 of 2 square root of 3 minus x. And over here, I've got the integral from -1 to 2 of x minus 1 plus the square root of 3 minus x. So at this point, guys, you can do the integrals. Thankfully, both of those inside functions, the 3 minus x, that's a linear, so it's really easy to handle with the u substitution. Here we're going to have x squared over 2 minus x, and this is going to be 3 minus x to the 3 halves times 2/3, and then I'm going to need a negative in here because it was a 3 minus x, and the derivative of 3 minus x is the -1. So in that u substitution, I would need to have a -1 in there, okay? And that's going to be from -1 to 2.
Is that x squared over 2 minus x times 2?
Minus x minus 2 times 3 minus x to the 3 halves over 3. I got it a little bit crammed there, sorry.
Right.
Okay?
So it's 2 times 3 minus x to 3 halves, because that's just the integral of the square root.
Yeah, that's the square root part there. Okay. So this is all that. This is obviously this. And that's that. Okay? But we also need to take the integral of this. So 2 to 3. The 2 is just going to be along for the ride. the 3 minus x is now going to be the 3/2 power times 2/3, okay? But I also need a times -1. Oh wait, I'm taking the integral, so I don't need that symbol here.
In physics, are we allowed to use the calculator?
In this case, we don't absolutely have to, but my guess is you would probably be allowed to use a calculator on this one.
So on the test, we will be using calculator?
I'm not going to guarantee that, but
What?
you could do this one by hand. And it's just a matter of how much you would simplify, okay? Because we do have a cube and then square root with that 3/2 power on both of these, okay? But as you simplify them, you know, you're just plugging in 2. So 4/2 minus 2 times 3 minus 2 is 1 to the 3/2 over 3. Okay? So you have that minus, and then I've got to plug in a -1. So that's going to be 1/2 minus a -1, so plus 1, minus 2 times, now this is going to be 3 plus 1, so it's 4 to the 3/2 power over 3. Well, 4 to the 3/2 is the square root of 4 times 2 cubed. Square root of 4 is 2, cubed is 8, times 2 is 16. Alright? So I've got 2 minus 2 minus 2/3. That whole thing is a -2/3. Okay? I have a minus 2/3. And then here I have a minus, this is 1.5 minus a negative, so that's going to be plus, and we said that was 16 over 3. Okay?
I'm a little confused about taking the integral of the 2 times root 3 minus x.
Okay. Let's finish evaluating, we'll come back to that in a sec. So now if I'm doing from 3 to 2, if I plug in a 3, this whole thing equals 0, right? Because I have 3 minus 3 is 0. Okay? So now minus, if I plug in a 2, I have 2 times -2 already, so that's a -4.
It's gonna be -4.
And 3 minus 1 is just 1 to the 3/2 all over 3. Okay? So that's just a plus 4/3. Okay? So, put this all together now. -2/3 plus 16/3 is 14/3 plus 4/3 is 18/3, which is 6. 6 minus 1.5 is 4.5, which was the same answer we got,
And a way longer process.
but it got a bit more complicated. Alright? So you can see here how using horizontal rectangles can be helpful if you're given things that are defined in terms of y. You just do right minus left instead of top minus bottom. Okay? But the process is still the same. The other thing that's you have to be careful about is make sure you use y coordinates, here the -2 and the 1, as your bounds, as opposed to over here you're using x coordinates as your boundaries. Alright, that's the other thing you gotta be real careful with. Okay? Now, let's revisit that just real quickly. The integral of square root of 3 minus x. That's u is 3 minus x. Right? Du is going to be -1 dx. So if I throw a negative there and a negative out there, the integral of something to the 1/2 is that something to the 3/2 divided by 3/2,
2/3.
and then I have that negative.
Wait, divided by 2/3.
No, it'd be
divided by 3/2.
divided by 3/2 times
Excuse me,
2/3.
Multiplied by 2/3. I'm
Mhm.
sorry.
Yeah.
Oh, you know what?
So
Okay.
that's how we got this -2 times 3 minus x to the 3/2 over 3.
The 2 up front threw me off.
Yeah,
I really threw it, and then also I think I messed up my substitution.
okay.
I didn't.
Yeah.
I didn't put them extra minus.
It's a good review for us, so.
Alright, thank you.
Okay, so just real quickly here, integration as an accumulation. We're adding up areas, okay? If I were to take the integral from -2 to -2, like in this first one here,
Oh wow.
I'm taking the integral, or I'm finding the area of essentially a point or a line segment, right?
Yeah, -2 to -2.
So you guys know that that's 0, okay? If I were doing it from -2 to -1, all right, we're finding this area here, okay? And in this case, that would be 5/3.
Oh, is it saying that you can do it by like right triangle trick?
If I went from -2, no,
Oh.
-2 to 0,
Oh, because it's not a straight line number.
we're just saying as you go, and this is something that, I mean, is kind of intuitive here if you think
Oh, so
about it.
It gets larger.
But yeah, the further you go, the bigger your area is going to get. 5/3, then 16/3. Okay, if we go from -2 over to 1, all right, we're accumulating even more area, so now we're up to 9. And if we go from -2 all the way to +2, that's going to be the greatest, and that's 32/3. Okay, so just a little illustration. We're accumulating more and more area, so long as that function is above the x-axis. Okay,
Yes, sir.
so not a huge thing, but just a little illustration there.